Hello to everyone. Today we are going to have a seventh lecture that is on LU factorization of a tridiagonal system. Well, when you have a linear system, Ax is equal to B, A is the coefficient matrix and B is the unknown vector where the values are given and X is the matrix to be determined. So the unknown vector, in the sense, it is a balancing vector and balancing values are given. So essentially B is also known to us, only the unknown is X. So in order to find out the solution to the system Ax is equal to B, we try to decompose the matrix A into easiest form so that we could able to find out the solution. That is the basic agenda of the decomposition. Now the input is, you see over here, the original matrix is given and output we do expect it as unit lower triangular matrix L and upper triangular matrix U. That is, L is the lower triangular matrix, and U is the upper triangular matrix, So we want to decompose the matrix A into L into U, product of two matrices, lower triangular matrix and upper triangular matrix. Let us say we set U1 is equal to A1, right? And for I is equal to 2, 3, etc. n, do this Li is equal to Ci upon Ui minus 1, where Ui is equal to Ai minus Li Bi minus 1. Right? And then we end this loop. So in this process, what happens is, when you set A11, that is A1 is free from 0. That means essentially this A11 should be free from 0. A22 also should be free from 0. A33 also should be free from 0. So that we could able to find out a solution to the system. So the algorithm looks very simple, but then it presents serious difficulties. So look at this matrix T, A1, B1, like that you do have a 0, C2, like that you have a Bn minus 1, 0, 0, etc. Cn. So the A1 is the one block, this is the block, and this is the another block, right? And this is the another block, right? So you will have a different blocks, and Cn also, it is another block, and this is also another block, right? So you have all the blocks. So I wanted to write this as identity matrix I, and this is L2, L3, Ln, and this is 0, this is 0, and this is 0, and this is 0. Similarly, the matrix U1, that's the block, B1 is the block, and like that you do have a 0. Similarly, second row you do have. Similarly, n minus 1th row you do have. Last one is Bn minus 1, that is the block. And the last one is 0, 0, and this one is the Un, that is another block. So essentially, you do have many blocks, and ultimately I wanted to write this block as the L into U decomposition, right? The matrix L is the lower triangular matrix, and matrix U is nothing but this is upper triangular matrix as we did in the previous case. Now let's see the solution of Tx is equal to B. The solution of Tx is equal to B over here. Ly is equal to B and Ux is equal to Y. So that means successively we are solving L of Y is equal to B and U of X is equal to Y. So that means we are solving successively Ly is equal to B and Ux is equal to Y, and the solution of Ly is equal to B can be achieved by Ly is equal to B, and the solution Vx is equal to Y can be computed from block back substitution. So this is what is called the how do you obtain this block substitution, right? So this algorithm will give you the matrix X as the matrix through block diagonal matrix. Now let us suppose see that simple example. Let's see over here. You have a matrix T, right? The matrix T is of, see, look at here, 4, -1, 1, 0, and this is -1, 4, 0 and 1, and this is 1, 0, 2, -1, and this is 0, 1, -1, 2, and the right side vector B is 4, and this is 4, and this is 2, and this is 2, right? So therefore, the vector that is, suppose T is equal to this matrix, this is a 4 by 4 matrix. This is a 4 by 4 matrix. So the 4 by 4 matrix multiplied with a unknown X, and you do have a right side vector 4, 4, 2, 2. Now let's see what are the blocks you do have it. What are the blocks you do have it? Now if you see very closely, see that this is the one block. This is the one block. That is 4 -1, -1, 4, that is the one block, I call it as. Then this is the another block, that is 1, 0, 0, 1, this is the another block. Similarly, when you consider this matrix B, that is B1 block is nothing but 4, 4, and B2 is nothing but 2, 2, right? Similarly, this, what is this A2? A2 is this matrix, that is 2, -1, -1, 2, this is another block. So with this representation, we could able to get the matrices B1 block matrix and B1 block matrix, A2 block matrix, B1 block matrix, B2 block matrix. Now let's apply the previous algorithm what we wrote on the previous case. So what is that? Set U1 is equal to A1, that is the matrix is, that is 4, -1, -1, 4. This is the matrix. We set this matrix as 4, -1, -1, 4, this is the matrix. And solve L2, that is U1 times of L2, that is U1 times of L2 is equal to, that is I2, which is equal to 1, 0, 0, 1, right? Similarly, while computing this L2 is nothing but U1 of -1, so which turns out to be 0.2667, 0.0667, 0.0667, 0.2667. This is what I obtained over here. So therefore, you do have a matrix A1 and you do have a matrix the L2 and you do get the matrix U1 inverse is like this. So that means you have L2 you do be getting, and similarly I wanted to compute U2. U2 is nothing but A2 minus L2 of B. This is the matrix. So which you get as U2 is equal to, that is 1.733 etc. minus of 1.0667 minus of 1.0667, 1.733 etc. This is the matrix U2 you get. So this is the matrix U2, right? So you have got matrix U1, you have got matrix U2. So therefore, further if you go ahead, we could able to find out the solution to the system in the following fashion. Now look at here, block forward elimination. So we wanted to do the block forward elimination. What is the block forward elimination? So U2 times of X2, which will give me what you call Y2 minus B2 of X3. So I do get this matrix. So therefore, which implies this X2 turns out to be 1, 1, right? So therefore, now U1 X1 is equal to, you can write this as Y1 minus B1 X2. So this is Y1 minus B1 X2. You can write this B1 X2. So this you get as Y1 is equal to 4, 4 minus B1 times of X1. That is 1, 1. So it is 3, 3. You do get X1 as 1, 1. So therefore, essentially, you do get the matrix as 1, 1, and this matrix you do get as 0.6667, and 0.667, this is the matrix, you do get it. So that means the matrix is very close to the true solution. Let's see what would happen to the true solution when you write over here. Let's see what is the remark you do get by using Gaussian elimination with partial pivoting. So Gaussian elimination is without pivoting, that is, you see here symmetric positive definite matrix. So you do get what you call symmetric positive definite matrix. So the number of iterations you do get over here is 2n cube by 3. Suppose the matrix n is equal to 3 by 3 matrix. That means you do get as 2 into 27 by 2, which will be equal to 54 by 2, which is equal to 27. Right? So diagonally, so symmetric positive definite matrix and rho is equal to 1. So then we can call it as a stable algorithm. The algorithm becomes a stable algorithm. So diagonally strictly dominant. So that is 2n cube by 3, rho is less than 1. So still in this case also you do have a stable algorithm. It could able to give you the better algorithm. Right? And Heisenberg matrix is Gaussian elimination with partial pivoting, that is 3n square you do get, rho is less than n, then you do get what you call the Gaussian elimination with partial pivoting. It is a stable algorithm. So 3n square, let's say n is equal to, you said 3, 3 3 are 9, 9 3 are 27. Right? Here also you do get 27. 10, 10 10 are 100, 100 into 3 it is 300, and in this case here 2 into 10 into 10 into 10 divided by 3. So it is it's a it's a 3 3 are 9, let's say 3 2 are 6, 60, 600 it is. See here it is 100, here it is only 600. So that means higher number of flop count is required in this case. Well, if you look at this case, similarly when the matrix is Heisenberg, still it is a stable, and then the matrix is tridiagonal, it's a big O of n, you do get what you call stable. Gaussian elimination with partial pivoting. Now we have seen Gaussian elimination with partial pivoting, what would happen? Gaussian elimination without pivoting, what would happen to the system of equations, right? So Gaussian elimination with partial pivoting, that is rho is less than or equal to 2, that is stable, and the Gaussian elimination, this is also a stable. So this is the growth factor. So we wanted to see the growth factor, how actually it would influence the system. We are writing this as the stability in terms of stabilities. That means the rho is less than or equal to n, that is rho is less than or equal to. So since we are talking about the 3 by 3 matrix, so rho is less than or equal to 3. So then you can call it as a Heisenberg matrix will become a stable algorithm. For in the case of this trigonal matrix, you see here, this becomes a stable algorithm even when rho is less than or equal to 2, we should be able to get the stable algorithm. Fine. So next, how do you compute the sensitivity of the eigenvalues? How do you find out the eigenvalue is sensitive or not? Look at here, let x inverse Ax is equal to diagonal of these things. That means you have a diagonal d lambda 1, lambda 2, lambda n, and everything is 0. This is the diagonal matrix. The number 1 over S of I, where S is defined by S is equal to mod of yi transpose xi, is called the condition number of the eigenvalues. This is what we call it as a condition number. So this is condition number. Condition number. So the condition number of this matrix A is equal to 1, 2, 3 and 0.99991, and it is 0, 0, 2. So therefore, you see from these eigenvalues, either it is 1 or 2.99, because they are sitting in the diagonal matrix. So lower will be zeros, upper will have it. So you do get what you call lower triangular matrix. So for a lower triangular matrix, so you can able to find out the eigenvalues, they are all leading diagonals. So lambda is equal to 1, lambda is equal to 2, lambda is equal to 0.999. Well, having had this definition, next is we compute eigenvectors corresponding to the eigenvalues. So when you compute these eigenvectors, look at here. So because in the previously you said there are 3 to 1, 2.990. That means lambda 1 is equal to 1, lambda is equal to 2, lambda 3 is equal to 0.999. This is the lambda 3. This is the lambda 2, this is lambda 1. So you can form this matrix corresponding to lambda is equal to 1 or lambda is equal to lambda is equal to 3, and this is the matrix you do get as x is equal to 1 minus 1 0.9623 0.0005 and 1.1923, and this is 0.1923. You get x. So I can write this x inverse ax is equal to diagonal entries. So that means I can write it as x inverse ax is equal to diagonal of the 1.9990 to, like this you do get. This is what the matrix I do get by using this, the computed eigenvalues. So the computed eigenvalues corresponding to one value is this column, second value this column, third value this column. So the system will become a very sensitive system. So we should be able to check that 1 by lambda, 1 by s of I is less than or equal to x2, that is 2 norm of x2, x2 inverse is equal to condition number of 2. So that way we can define what we call the condition number. Well, next, QR factorization. So one of the most interesting thing available in the linear system is the matrix A, how you can decompose into factorization of two matrices. That's what we call it as a QR factorization of the matrices. You find applications, the QR factorization, image restoration and image construction and image biomedical engineering, computer tomography, and so on and so forth. There are many areas where you be interested in the finding out the image processing applications by using the QR factorization. So we will define in the following way: a square matrix O is orthogonal to matrix if and only if this inequality happens. That means O times O transpose is equal to O transpose into O is equal to, so identity matrix, which we call it as orthogonal matrix. So we can define in the following fashion: given an m by n matrix A, there exists an m by n orthogonal matrix, that is given a m by n matrix, and there exists a orthogonal matrix X such that Mn, that is upper triangular matrix R, such that A or A is equal to Q into R. So we should be able to construct an upper triangular matrix R such that is A is equal to Q into R. So R is what is called rectangular matrix. Q is called the matrix which we wanted to obtain a new method which we were able to find out the QR factorization of the matrices. Well, let's go further. Computerization of QR factorization. What are the methods available in order to find out the QR factorization? The most famous one you see here, householder method. The second one is what is called Given's method. Third one is what is called classical Gram-Schmidt method. Fourth one is modified Gram-Schmidt method. So there are some instances where actually householder method works very well, and there are some instances where given method works very well, and there are some instances where classical Gram-Schmidt method also works very well, and there are some instances where modified Gram-Schmidt method works very well. So therefore one should be very careful. How do you handle this the classical methods to find out solution to the systems. Now let us look at into one by one. Householder matrices and QR factorization. Quite often we use in many engineering applications, that is householder matrices and QR factorization. Let's look at into householder matrices and QR factorization. So let us define formally a matrix of the form H is equal to I minus 2U times of U transpose upon U transpose of U. So that will be the matrix where U is a non-zero matrix in R and also called elementary reflector or householder transformation. So the transformation is called elementary reflector or householder transformation. So we could able to obtain the householder transformation by using what we call the elementary reflector. So elementary reflector or household transformation. So the algorithm is very useful. You can find it applications in many engineering systems, right? Especially control systems, image processing, image restoration, noise removal, and so on and so forth. So what is the algorithm? Input is a non-zero vector x. X is a non-zero vector, and the output what I do expect is a vector u such that I minus 2u times of u transpose upon u transpose u times of x is equal to the x000t, where x is any non-zero vector. This is what is called the householder transformation for the pure factorization. Next, let's see how this algorithm works. So step 1 is, that is, find the scaling factors m, that is maximum of x1, x2, x3, xn, right, scaling factors. And step 2 is scale the vectors as follows, that is for I is equal to 1, 2, etc. up to n, do xi is equal to xi upon m, and do and for. So this is and for. So whenever you start with for, this should be also, there will be and for. Then only the program will become a meaningful. Compute the householder vector u, that is u1, u2, u3, un transpose, and u1 is equal to x1, that is x1 plus norm of x of 2 sine of x1. Okay. For I is equal to 2, 3, etc. and do ui is equal to xi, and well, let's see this example, simple example. Let x is equal to 0, 4, 1. Right? X is equal to 0, 4, 1. You see this example, and m is equal to 4. This is the maximum element. So m is equal to 4. Step 2 is x1 is equal to 0, that is the element. X2 is equal to 1. X3 is equal to 1 by 4. So you do get as 0.25. And similarly in step 3, you write x1, u1 is equal to x1 plus norm of x2. You do get this as 1.0308. And u2 is equal to x2, u2 is equal to x2 is equal to 1, u3, x3 is equal to 0.25. So therefore the matrix U is equal to u1, u2, u3 all transpose. So it will become 1.0308, 1.25. Right? So they will verify this. You can also verify that this will give you a nice example how you can able to find out I minus 2u u transpose u times of x, and this unknown vector x will be known by using this example. So let us look at into household pure factorization, right? So the matrix A is equal to, you see, very sensitive matrix, because compared to this element, what is this element? A11 is 1, A12 is 1, A21 is 0.0001, A22 is equal to 0. That means this is a very small element in compared to 1. So by using the pure householder method, we can compute H1. So H1 is nothing but H1 is equal to I minus 2u1 times of u1 transpose upon u1 transpose into u, and x will be like 1.0010. So you get the value of x1, right? Well, next computation will be u1. So u1 is equal to this matrix plus, and I substitute those elements and multiply with a1. So I do end up with this matrix 2.00012. So this is a bigger value. This is the smaller value. Smaller value, that is apart from the 0. So you do have a1 is equal to h1a I minus 2 u1 transpose into a. So you get this matrix, right? Now let us look at into the step 2. So when you go to test step 2, compute h2. So h2 is equal to, again same stuff. h2 is equal to I minus 2 u2 times of u2 transpose upon u2 transpose times of u2. So I can compute u2 is equal to this matrix, and when I multiply all these things, I should end up this h2 prime is equal to this matrix 0.7071, 0.7071, 0.771, 0.7071. So therefore, ultimately I could able to write this h2 as this matrix. See here, this is not changed, this is not changed. So this lower 2 by 2 will be changed. Next, see that A2, how do you compute in a similar fashion? A2 is equal to H2 times of A1. So you do get these values. Minus 1, 1, 0, 0.001, 0, 0. That is what is called. So similarly, you can find out Q is equal to H1, H2, you get this matrix. So this is the R matrix which you obtain. So minus 1, 0, 0.001 and 0, 0. This is the matrix where R. R is also, the determinant of R is free from 0. We could able to find out this matrix R. So by using QR factorization, we could able to find out Q as well as the matrices R. Move ahead. Classic. So let's look at into, in contrast to the one which we did it now, we will look at into the classical Gram-Schmidt algorithm. How it works, how it would be efficient in compared to the previous methods. Let us define before going to that orthogonal sets. Let V be a vector space with an inner product, non-zero vectors V1, V2, V3, Vk, which are set of belongs to V, and form an orthogonal set if they are orthogonal to each other. That means V1 is V2 is equal to orthogonal to the orthogonal of for all I not equal to j. So we should get the orthogonal vector. So in addition to that, if all the vectors are unit normal, that is norm of Vi happens to be 1, that is, then the vector we are said to be orthogonal vector. These are all orthogonal vectors. So you do find out orthogonality in many engineering applications. So if the vectors are unit normal 1, then we can say that the vectors V1, V2, V3 are all orthonormal vectors. So if they are orthogonal, we will have a very specific applications which we get into in science and engineering. Now let us state a theorem, that is, the theorem is very useful in trying to find out the orthogonality of the vectors, right? What is this theorem is, any orthogonal set is linearly independent. You see here, any orthogonal set that is linearly independent. Let X be a vector space with an inner product. Suppose x1, x2, x3 are in V. x1, x2, xn. They are all belongs to set V. Now let V1 minus x1. This is the first step which we do it. Second step is whatever we got it, we use it. Third step, fourth step, like this. So it keep on do like this. These are all vectors are actually orthogonal vectors. You can verify and you can check by multiplying those vectors. It will become an orthogonal vectors. So V1 is known, V2 is known, V3 is known, V4 is known. So then V1, V2, V3, V4, Vn is an orthogonal basis. That is fine. Now let us look at into the other issues. Any basis, so we write it x1, x2, x3 orthonormal basis of V1, V2, V3, Vn. So we have a theorem. The theorem will give us very elaborative explanation. Any finite dimensional vector space with an inner product is an orthogonal basis. So that means we can also define any orthogonal basis, any finite dimensional vector space with an inner product has orthogonal basis. So what is the remark over here? An infinite dimensional vector space with an inner product may or may not have an orthogonal basis. Look at over here, very interesting example. We comment. An infinite dimensional vector space with an inner product may or may not have the orthogonal basis. So you are not very guaranteed, although the dimensional vector space is infinite, right? Fortunately that we are not getting much destruction. Otherwise you need to check every time. So the moment when you are keep on checking, there is a flop counts. So it will add it to your error, which is not a desirable situation. Let's see this example. Let phi be the plane in R3 spanned by the vectors 1, 2, 2. Let x2 is equal. Find an orthogonal basis, orthonormal. So let x1, x3 is a basis for the element gamma. We have extended to a basis for R3 by adding one vector from the standard basis. This is the vector you do get this vector. So that means whatever right hand side vector is there, we are added to this vector, and this is the subvector of this, which determinant is free from 0. Well, using the Gram-Schmidt process, we could able to orthogonalize the basis x1 is equal to 1, 2, 2, x2 is equal to minus 1, 0, x3 is equal to 0, 0, 1. So V1 is equal to x1, that we can set it from the previous algorithm. So V2 is equal to x2 minus of x2 V1 x2 V1 upon V1 V2 multiplied with V1. So you do get this vector. And similarly for V3, you do get this vector. So now V1 is equal to 1 to 2. So we have to need to check it whether it satisfies or not. Is it orthogonal basis or not? So we get as V1 is equal to 1 to 2 and V2 is equal to minus 4 by 3, 2 by 3, 4 by 3. V3 is an orthonormal basis for R3. So we could able to get this vector as R3. That means V1 is obtained, V2 is obtained, V3 is also being obtained. So V1 is an orthogonal basis for pi. It remains to normalize these vectors. So V1 is this thing, V1 V2 is this thing. So that is simple V1 V2, V1 V3 is this thing. So only one vector will become orthogonal vector. Therefore, W is equal to V1 upon norm of V1. So similarly, W2 is equal to norm 2 by norm of V2. W3 is equal to V3 upon norm of V3. So we can be able to compute the orthonormal basis for any vectors where these vectors will become a vital role, right? So today what we learned was, we started with what we call the Gram-Schmidt orthogonal process. We also defined a classical Gram-Schmidt orthogonal process. We also have seen the QR factorization and what are its variants of QR factorization. If you are going to use straight away, so what would happen to your program and your really, so that's what I am very much interested to know the level of understanding what you have it. So with these words, I will stop this lecture. So I'm sure that in the assignment will be uploaded, you would be learning many more things. Thank you very much.